In the next section, we'll look at a second way to use the fractional solution and round it somehow. And we bring back randomization here, which is yields different performance guarantees. I guess it's not obvious which one is stronger in general. The idea behind this is, especially if the values, like in our set cover case, are between 0 and 1, you could pretend they're probabilities. Or intuitively, if the fractional solution includes a set, gives a set a certain value, you could say this is a probability that you want to take that set. And so you can just do that. And the cool thing about that is that if you take the expected cost of the sets you get, of the collection you get, that'll be exactly the optimal fractionals objective value, just by definition. I guess assuming here that we have numbers between 0 and 1. And so that sounds maybe too good to be true, because we know we can't usually achieve the value of the LP. And indeed, most of the time, if you just randomly pick the collection like this, you're not going to get a feasible solution for the integral problem. But we'll see that you can often still get something out of this idea. And here, if you think in the context of set cover again, if some element in the universe occurs in a certain number of sets, then the probability that it is covered is 1 minus the probability that it is not. And the probability that it is not covered is the probability that for all the sets where it occurs, we don't pick that set, right? And that you can write, because we've picked the probabilities just to be these variables for the sets. It's 1 minus the product of 1 minus the variable. Now that sounds maybe not like you could do much, but you can bound it. Such a product is always minimized because it's kind of a convexity argument. It's minimized when you have the same value for all the xj's. And in particular here, because they're between 0 and 1, 1 over fe is, because you have the constraints from, so you're using convexity and the constraint that all these have to sum to at least 1. To bound it like this, then this is our seen that inequality many times before. This is in the limit goes to e, and for any finite value is below kind of the repeated interest thing. So you can lower bound the probability that a specific element is not covered if you just pick a random set cover candidate like this by at least some constant. It's not with high probability or anything, but it's also not 0. And so if you repeatedly draw such set cover candidates, this question turns into a kind of a coupon collector scenario. If you keep, the assumption is that you keep all the sets that you've ever chosen, and just keep adding to your candidate set. Then if you do that for roughly log n repetitions, you should cover all the sets. Then you've collected all your coupons. And it's curious that this same harmonic number pops up. That term, if you remember, that was the approximation ratio of the greedy set cover algorithm. The reason to look at it again is that the methodology here is more general than set cover. So how can we make this work? In particular, we're using this randomized rounding from before and repeat it many times. So here R is the number of repetitions. So you see this is the outer loop, but we're computing one candidate set. So we do R iterations, but then for each of the iterations, we go through all the possible sets in our input and add this set with a certain probability to this candidate set Ci. And at the end, we return their union. So any set that was picked in any of the R iterations is going to be part of the final solution. From this hand-wavy argument, maybe we should expect some logarithmic number of repetitions to be the right choice. And well, it turns out to get the numbers right, you want to use a slightly bigger number than that. So it's not ln n, it's ln n plus a constant. Right? And if you do that, then this algorithm produces a feasible set cover. That's indeed a set cover and deserves this name with probability at least 3/4. And we've done most of the work for the proof. The probability that a certain element is not covered was bounded by this 1/e. We've argued about the counter probability previously, but it's more convenient to write it like this, because this is the probability that a single element in the universe is not covered. To get a bound that none of the elements is not covered, we take the union bound over all of those elements. So the probability, this was for one iteration. If we keep repeating this r times, then we get the rth power of this, that it's not covered in all of the repetitions. So this goes down a lot with r. And the union bound then is that the result is not a set cover, it's just the factor n times this. So if you set r to natural log of 4n, this works out to exactly 1/4. Okay. Now this is the probability that we get any set cover. The other question is, how good will it be? And the expected cost is what we can bound. If we produce a set cover with this previous algorithm, then the expected cost it has is r times the optimal solution. So we essentially pay the same factor here. If that's the case, then this is only about the expected cost. We can, as always, use Markov's inequality to turn that into a success probability when we scale up the expectation a bit. So in particular, 4 times the expected size, the expected value will give you a probability of 1/4 to be above that. That's more what we're going to use on the next slide. But let's first prove this in the general sense. Our algorithm picks the final solution as the union of r repeatedly chosen things. These are all identically distributed and independent. For the cost of the final result is at most the sum of the cost of all those elements summed up. It'll probably be a bit less because we repeatedly draw some sets, but it's hard to analyze, so we'll just upper bound it generously. Then we use linearity of expectations and move that in. And because these are r identical repetitions, each time the expectation is as we've calculated before, the optimal LP solution. That's how you get this r times as in the claim. Okay. Now this is not a randomized, this is not an approximation algorithm in the way we defined it, because it sometimes returns a solution that's not actually a solution. It's not even feasible. In this case, that's easy to fix by, if the algorithm fails, just taking all sets. So you run your randomized rounding. If the output is garbage, then you output all of the sets, otherwise you keep it. And with that, you can show that this is a randomized 4 log n approximation for set cover. And we've basically done that. So you just have to prove that with probability 1/2, right? This was the definition. Randomized blah blah approximation means with probability 1/2, the approximation ratio is below this bound. And for that, we have to bound how often we return the entire set, because we cannot say much about its quality there. So the probability that C is not a set cover, which means we return something of bad quality, or that it is a set cover, but it actually is of poor quality itself in terms of the cost. That's the union of 2 events. I can upper bound that union bound by the sum of the probabilities. And both of these we've just bounded by the previous lemmas. So this was that the algorithm doesn't output a set cover, and this was the Markov inequality from the previous slide. So in total, with probability 1/2, we get something that's at least as good as that. And with probability 1, we get something feasible.